The focus of this PhD study is the analysis of navigation structures for future UAV traffic management, or UTMs for short. Current UTM systems typically use a centralized volume reservation approach to maintain separation between agents. In this work, we consider a distributed control method for traffic management, which does not rely on a centralized entity for individual agent coordination. We achieve this by using a simple rule-based algorithm that uses global information and information from local agents. In this simple control method, known as free flight, agents move to their destination while communicating with each other to avoid collisions. In a classic collision avoidance method used in many robotic fields, a repulsive force is applied to maintain separation. One of the contributions of this work is the development of a collision avoidance method that causes agents to maintain separation orthogonal to their direction of motion. This is like TCAS in civil aviation, however, is applied in whichever direction is orthogonal to the agent's plane of motion. Returning to free flight, as densities grow, agents spend more time avoiding collisions, making the system less efficient. This is compounded by large conflict distances. One contribution of this work is the development of a rule that encourages emergent lane formation. In this simulation, emergent lane formation causes agents to follow behind each other, thus reducing the collision rate. Furthermore, as agents spend less time avoiding collisions, the average speed is greater, hence increasing the efficiency. This is effectively a win-win. This result is mainly true when there exists a bulk flow in the system, where many agents are traveling in similar directions. Within a UTM, it is assumed that for most flights, agents will likely fly from a distribution center. Furthermore, no-fly zones will cause the paths of many agents to coalesce into small regions of space. This means that it is likely that lanes can be used within these regions of bulk flow to reduce the risk of collision and increase efficiency under high enough densities. The natural continuation of this is implementing and evaluating the performance of a predefined aerial routing network. In this work, several types of paths are proposed, namely lanes, ribbons, and corridors. A novel type of path is a helical tube, where agents move in a helical motion. In the implementation of aerial routing networks, paths have low risks of collisions, while intersections have a considerably higher risk of collision. The performance of various intersections are analyzed using a dimensionless conflict rate. An intersection with a low conflict rate relies less on collision avoidance methods and is inherently safer. It was found that helical tubes had lower conflict rates than corridors, however, a smaller capacity. Practical experiments were performed to compare simulations to a real-world application. The experiments showed that the aerial routing networks performed consistently with simulations. The final contribution of this work is the development of a congestion metric. This metric measures the expected risk of collision in a particular region. Several potential implementations were compared, and an adapted gas kinematics method was found to have the strongest correlation to collision risk. This metric was implemented in several test cases, including a procedurally generated city. Here, the congestion metric is presented as a heat map to show regions of high and low risk of collision. In summary, this work has developed and tested a novel collision avoidance method, implemented and evaluated aerial routing networks, and advanced a congestion metric to be used in UTMs. The key learnings from this thesis are: for low densities, navigation structures are not required. However, as densities grow, navigation structures can increase efficiency and simultaneously reduce collision risks.